John Mitchell. I'm the head of the Department of Electronical Engineering here. It's wonderful to see so many colleagues, friends of the department, and students who are able to be with us to hear this inaugural lecture this evening. Inaugural lectures are a wonderful part of what we do within a university, where we have a chance to celebrate our colleagues' achievements and the promotion that they've received to the standing of professor. And this evening, it's absolute delight for me to introduce our colleague, Professor Oleg Mitrofanov, and to celebrate his elevation to professor. Please come in. Oleg has been with us in the department for a number of years and manages the ultra-fast laser laboratory, where he conducts experiments around Terahertz characterization tools and observing Terahertz magnetic fields and ultra-fast processes in materials and electronic devices. And over the course of this evening, I'm sure we'll hear more about both the fundamentals of those, but also some of the really interesting and novel applications that Terahertz and the signals that he generates and characterizes are useful. Oleg.
Thank you, John, for a very nice introduction. It is a really pleasure to give this lecture. I know it's been some time since the actual promotion to the professor, but it's been COVID and it's been so many other things. So now it's time to actually talk about what I've been doing here for the last almost close to 20 years. And so most of my research has been in terahertz. For those, it's very nice actually to see very young faces in the audience. So I will try to, in the next few slides, very gently introduce what is that this topic is about and what are the terahertz waves. For those who already know it, so there's no surprises. You probably have heard a lot of things that I periodically talked about in hallways and laboratories. But nevertheless, it's really a pleasure to kind of go and look through all the various developments in the field. So what I wanted to do today is not only to kind of show the research that we've been doing, but also give a little bit of an introduction, my view on this field. And I've got to say, it's also a pleasure to see a lot of people here who has been working with me. And I also appreciate that some of the people joining online to watch this. So it's really a pleasure to talk about this research, knowing that a lot of people contributed to this work. And it's also been actually a lot of fun doing this research. So for those young people in the audience who are considering maybe a career in academia, even though it's hard, but it's actually a lot of fun. Okay, so I'll just start with my presentation. So what are these terahertz electromagnetic fields, and why do we need to try to unveil what's happening there? And as you probably know, it's part of the electromagnetic spectrum. And if we look at our electromagnetic spectrum, they're sitting right there, kind of between the visible and microwaves, right? So we all know that at every part of the electromagnetic spectrum, we could see something different. We're so much used to seeing the universe in our visible part of the range, electromagnetic range. But if you look at things at other frequencies, there's lots of other different phenomena that you'll be able to see. And that was effectively what kind of drew me to this field. There was this new field of terahertz research, and there was really very little known about that. Very little known what kind of, how the world looks in those terahertz waves. So that's what drew me to start doing research in this. There's no shortage of good examples of how things look differently at different wavelengths. You could look at one of the first X-ray photographs by Röntgen, and you can see that, you could possibly see the bone structure. Well, another example is the map of the temperature, which showed the heat wave a few years ago here in Europe. Or if you go to microwaves, you can actually see interesting phenomena as the cosmic microwave background. So within all these different ranges, you can find different phenomena. This is what the technology and science is trying to do, especially it's trying to look at the world with slightly different wavelengths. So if we look at terahertz, we can actually, there's no better place to start than looking at our universe. What are we going to see with terahertz waves? Turns out actually there's quite a lot of emission coming from outer space in terahertz frequencies. It's a bit different from cosmic microwave background, but it still tells us something about what's happening in the universe. It happens that most of the dust and interstellar matter happens to be at a temperature of only about 15 to 20 Kelvin. And the thermal radiation from this dust matter actually has a peak at terahertz frequencies. So within that part of the electromagnetic spectrum. So by looking at the distribution of this interstellar matter, people can predict where, for example, the star could be formed, right? So this is out in space, but here on Earth, we have other things to kind of worry about. And here's, I just brought up a couple of examples of things that have a specific kind of response or specific phenomena at terahertz frequencies. So electron hole plasma, that's what we see in most of our electronic devices, actually has a very specific response in terahertz frequencies. Molecular rotations are well known to have specific quantum mechanical lines that appear in terahertz frequencies. Phonons, excitons, plasma polariton. I'll talk a little bit about some of this later during this talk, but this is just kind of an overview that there's a lot of fundamental science that you could probe with terahertz waves. So until about maybe 20, 30 years ago, there was really not much of technology that could actually access this frequency range. So there was few instruments, but they were not particularly sensitive. And in the last about 20, 30 years, there's been a lot of development. And it's really actually nice to kind of look back and see how much has become possible to do and what's possible to do now. And also, with the development of the technology, various devices started appearing, starting with waveguides, resonators, matter surfaces, sensors, and eventually leading to applications. So probably some of the applications that potentially would be developed in the next 10, 15 years, communications and maybe environmental monitoring, that's where the terahertz waves could be quite useful. So what is the terahertz wave and why it has been so difficult to detect it? So we know that it's just an electromagnetic wave, so electric field, magnetic fields oscillate as a function of time. But if you take a look at how it looks like, for example, this is a temporal axis, time axis going up, and this is our electric field going up and down. So the changes in the electric field happen on the order of a fraction of a picosecond. And that tends to be too fast for any electronics to detect. And this is why it's very difficult to detect these waves with normal electronic instrument. If you have an oscilloscope, you can try to detect, but basically will not have response in those frequencies. If you look at the other ways of detecting, like for example, a photodiode, you'll find that the energy of the photon for the terahertz waves is quite small. It's actually smaller than the thermal energy. And therefore, most of the devices, there's no really photodiodes that would operate for these photons. So therefore, there needs to be something different in order to detect these waves. And luckily, a couple of interesting technologies been developed about 30 years ago. So one is the ultra-fast femtosecond lasers. And it's quite a remarkable type of a laser that produces pulses with a very regular interval and extremely short. So what you see out of this laser is optical pulses that come at regular intervals. And you could use it effectively as your clock. So you can specifically turn on and turn off something in your system with this laser. At the same time, people were trying to develop ultra-fast materials, so materials that can respond very fast electronically, and develop what's called fast photoconductors. One of them is low-temperature ground gallium arsenide, which is a typical gallium arsenide, but it has additional defects in it. arsenic defects, they tend to make the lifetime of the carriers very short. And as a result, this material responds very quickly to electromagnetic waves. So with these technologies, it was possible to start detecting terahertz waves. It was also possible to generate terahertz waves. This is an example of a terahertz pulse, and that's the type of wave that we'll mostly be discussing in this lecture. So how would a detector would work? It's actually a very, very simple device, even though there's a lot of technology that goes in there. But you can imagine just two metallic contacts with a semiconducting gap in between. And the material that sits in that gap has what we call a very short lifetime for the carriers. So if you turn them on with light, they only exist there for about a fraction of a picosecond. And therefore, if at the same time you'll send a terahertz wave, or any type of wave, that will induce a bias between these contacts, and you send in this optical pulse from the ultra-fast laser, it will basically shorten that circuit for just a very fraction of time, and you can measure the current that runs in that circuit, right? And that current runs for only a very short period of time, so you can delay the distance between your incoming terahertz wave and optical pulse and effectively sample the electromagnetic field, which varies very fast, but you can sample at a very, very precise high temporal resolution. So it is maybe a bit of a complicated technique. It's a little different compared to just putting a photodiode and measuring current, but it does give you that temporal resolution. And let me just show you what you could do with this temporal resolution. So these are typical pulses that we can generate with using this technology in detect. So it's a very short pulse, has pretty much just only one cycle of electromagnetic field, which also implies that it will have a very large bandwidth of frequencies. So if you take a Fourier transform from this pulse, you'll find that it contains actually a lot of frequencies from about a few hundred gigahertz up to a couple of terahertz. That means that there is electromagnetic energy with all this spectrum. And you can use this for spectroscopy and imaging, so that is what we're going to try to use it sort of during this lecture. Okay, so this is just a picture of one of the devices that can be made and can detect terahertz wave. It has a little silicon lens, and all that structure is basically sitting underneath of that tiny little dome lens. Right, so it's actually a very simple device, but they are extremely reliable. And for a long time, it was pretty much the only technology that allowed us to measure these terahertz waves. Okay, so as I mentioned, it's a short pulse, right? And let me illustrate how you can do the spectroscopy with this pulse. So what I'm showing here on the graph is two waveforms of this terahertz pulse. You can see the black line shows a pulse that passed through about that distance of space, which has been purged with nitrogen, so it doesn't have any water molecules in there. And the second, the red one, is the same volume of space, where the pulse has passed, but filled in with just normal air, like, for example, we would have today, which have a small amount of humidity. So maybe a couple of % of molecules in that air, in addition to nitrogen and oxygen, would be water, right? And you'll see that the pulse changes its shape. Instead of being relatively kind of subdued right here, it starts oscillating. You could think that this is noise, but actually if you take a Fourier transform of it, you'll find out that these oscillations are very regular. And what they correspond to rotation of this molecule in space. So the molecule is in gas form, so it can freely move as it wants. But it turns out if the molecule has a dipole moment, so the electromagnetic wave can rotate this molecule and it will start rotating. And as a result, molecules, because of the quantum mechanics, will have only very specific frequencies in which they rotate. It's not like just a normal ball that you can rotate with any frequency. Quantum mechanics tells us that actually for a given mass of the molecule, it will be rotation with only specific frequencies. And these oscillations actually represents this rotation of the molecule. If we look at the Fourier transform of these waveforms that I just showed, what you'll see is a series of absorption lines. So these are frequencies at which energy is being transferred to that gas. Right? So pulse passes through air. It only at very, very selective frequencies it actually loses its energy and transfers it to molecules, which now starts rotating. You could also look at the refractive index, and it does experience this behavior, which is a classical behavior described by the Lorentz model, which is also really remarkable to see in the experiment. So very often, this type of measurement was a technology which doesn't have the temporal resolution, as we just described with this technique for detection. It's very difficult to determine this type of behavior for the refractive index of air. And if you look at the values that are there, it's a really tiny change in refractive index, 10 to the minus 3, 10 to the minus 4 of 1. So a smaller than a % change in refractive index, but it's possible to detect with this relatively simple technique. We're simply passing a pulse, a very short pulse through air, and look at its deformation. So this is the example of spectroscopy application. Now, if we can't see molecules that way, if we can see other phenomena, it would be really interesting to actually start using it as an imaging technique. And since it's only been pretty much a point detector, so there's no such a thing as an array that can give you an image like you would normally do in a camera. So it's a point detector, but if you have a point detector, you could move your object with respect to that point detector, and you can actually synthesize an image of something. And this is what's been done. Some of the first images that's been done is just to test what happens with Terahertz wave as it passes through something like a leaf. Right? Leaf contains some moisture, so part of it's going to absorb Terahertz wave, part of it's going to be more transparent, so you could see a difference in the contrast. Right, and that actually indicates that there is, with this technique, you can actually kind of measure the moisture content of this particular object. If it dries out, for example, after a couple of days, it will change the way it looks. Transparency of that leaf will change over time. So one thing, if you can take a little bit close look, you will notice that the image is not really that sharp, right? So now we can take a camera and take a much better image of the leaf. Why would we need something like this? And the problem here is the actual wavelengths at which we're doing the imaging. So Terahertz waves, they have a wavelength of a fraction of a millimeter, about 300 microns for 1 terahertz. And there is a diffraction of electromagnetic waves. Tells us that you cannot really make an image sharper than about a wavelength of light. So if we're dealing with optical waves, the spatial resolution that you can achieve with optical waves is on order of a micron, maybe slightly better than a micron, right? But if we're dealing with a longer wavelengths, like terahertz waves, where the wave is about 300 microns, then as a result, you cannot get an image better with the spatial resolution better than about a millimeter, right? And that you can imagine will limit quite a lot of the application space. So what we're trying to do is to figure out how to actually utilize this radiation and apply it to various objects that are much smaller than the wavelengths, and therefore kind of enable imaging of these objects. Interestingly enough, there's been some ideas of how to do that, and it's called near-field microscopy. And interestingly enough, I didn't know that at the time when I was studying this, but Eric Ash, who's professor and former department head in this department, actually did one of the pioneering work on this, and they did the first demonstration of this concept of near-field microscopy with 50 megahertz or microwaves, but it was still interesting that it was actually done here in this building. So there is a concept of how to improve the spatial resolution, and that's based on the idea that, okay, so we are limited by the wavelengths, but in principle, you could say, if you take a molecule, right, a molecule could be much smaller than the wavelengths of light. It can emit a photon, right? So if you move around that molecule, around your object, and again, you like synthesize the image based on various locations where the molecule is, and then sends the photon, and it passes and interacts with an object. So you can create an image, and that way to the diffraction image. So this is roughly the idea that is described with this work, and that's what we were trying to do, to apply this idea and to basically improve the spatial resolution for terahertz imaging. So, and then suddenly, if that were possible to do, that would open this electromagnetic waves to a lot of applications. So if you look at the application space, potential application space for all this phenomena like quantum, plasmons, or excitons, they all tend to be occurring in objects that are very, very small, much smaller than wavelength. So if it's possible to do the imaging at a sub-wavelength resolution, then suddenly you open up this waves to a huge application space, right? So the question, how can we do it? So if we actually take a small aperture and just create this very, very, very small sub-wavelength size source, we can estimate actually what's possible to do. So imagine you have an electromagnetic wave falling from the left-hand side, passes through that small aperture. And the question is, how much of light do you think is going to pass through the aperture? So if the aperture is larger than the wavelength, we can estimate it simply by the area of the aperture, say it's proportional to the area of the aperture, which is a very good approximation. But once it gets smaller than the wavelengths of light, additional reflection starts occurring in the aperture. And actually, the light that passes through the aperture starts decreasing very, very, very quickly. The problem was interestingly solved by Hans Bethe almost 70 years ago. And what they found is one of the strongest decays in transmission as a function of the aperture size. And you can see it here that, if, for example, if you take an aperture size that's about 1/100th of a wavelength, so for our terahertz wave, which has 300 microns, we'll try to pass light through 3 micron aperture. You'll find that the wave, the amplitude of the wave that passes through that aperture is going to be about 3 or 4 orders of magnitude smaller than you started with. And that's electromagnetic field amplitude. If you consider the power of the wave, usually we tend to measure like with intensity, that would be square of that, so 10 to the minus 8, right? So it's a very, very huge loss in terms of how much light is actually can pass through this aperture. So if you want to get to the level of a micron or 10 micron spatial resolution, you have to deal with incredibly high losses in incident power. And it actually pretty much becomes impractical. So it turns out that law is for what we know is propagating wave. So typical electromagnetic wave, they travel as a wave. But if you get very close to the aperture, there tends to be a little bit of additional energy that sits right next to it. And it's a non-propagating energy, right? It just exists right there by the aperture, what we call evanescent waves. And they tend to have a much higher amplitude compared to the propagating wave. So in principle, even for very small aperture, you can get relatively high amplitude of electric fields passing through this aperture. The trick is you just need to get very close to it, and that's very hard to do. So in order to utilize this effect, that's what we decided to do. And if we just estimate how much improvement you can get several orders of magnitude improvement in the signal that's going to pass through the aperture if it's detected right next to it. Or if you're thinking in terms of the resolution, it means that you can push the resolution to higher and higher values. So with this idea, we built one of the first collection mode microscopes. And this is sort of roughly a schematic diagram of what it is. So imagine an electromagnetic terahertz wave is coming from the bottom. You could have a sample, and you'll put this probe that contains a small aperture through which you can probe the electromagnetic waves. And right next to it, maybe within a micron or so, we'll need to place a detector, and then all of this is just will be, let's say, sitting on a transparent substrate, so we can actually send this optical pulse to sample those terahertz waves as I showed in the detection technique. So we built some of this first type of collection mode near-field probes, and we made some of the first images of, in this case, it was just a metallic pattern on a dielectric substrate. And actually, from just the first images, what we found is that it doesn't make any sense. So what we imaged here is basically metallic lines. So there's a parallel horizontal line this way and vertical that way. And they're not transparent to Terahertz waves. So what we normally would expect that is just going to be completely opaque. Area outside will be transparent, so we're supposed to see some fields here. But then it was really strange to observe actually presence of noticeable signal right at the metal, which we're supposed to have no signal. And it also tends to be changes with time. So at some point it has one polarity, and a little bit time later it has a second polarity. Actually, is one of the first images of Terahertz. Oops, how do I do that? Of what's actually happening. And what you could see is there's a little bit of excitation happening right at the center of this image, and then kind of spreads out to the side. So as it later it became clear that these were surface plasmon waves. At that time, again, something that's only been discussed very, very vaguely in the literature. Actually, I don't think I even knew the word surface plasmon at that time when I was measuring this. But this just shows an example how you could detect something with this new technology, and it shows something that you don't expect. And that's what initiates a little bit more investigations. And this curiosity of what is happening there is what very often leads the science to the next discoveries. Okay, so that was some of the first measurements we did when I was still doing my PhD studies with John Federici and Igor Brenner a long time ago. When I moved to UCL about 10 years later, I continued working on this, and we continue basically investigating these interesting waves. And we found that very often we see them on all the metallic objects, let's say a bow tie antenna, we see all these different patterns. We start understanding what is happening. So if you imagine this is a metallic bow tie antenna, and it's illuminated with an electromagnetic wave, let's say from the side of the screen, what happens is that right at the edges, it creates charges. It just induces charges right at the edges of this bow tie. So they normally don't like to be in this non-equilibrium situation. Once the wave has passed, this electromagnetic excitation has passed, now they start spreading out, and they spread out back to the metallic surface. This is where they can easily go to. And they move like waves, very close to the speed of light, but they move pretty much like waves. And what you see here is pretty much the standing wave pattern that's formed with this electromagnetic waves. They basically slide along the surface. And this is what is also known as surface plasmon waves. That's been kind of in the center of investigations for the last maybe 15, 20 years at all different wavelengths, including the Terahertz part of the electromagnetic spectrum. And we did all this work with my first PhD student here, Raymond. Some of you probably remember him. This is another experimental observation of a very similar phenomenon. It kind of like shows a little bit how an electromagnetic resonance can be formed on a metallic antenna. So imagine this is the same bow tie antenna we just talked a little bit about. But on this map, we're not just showing the two-dimensional distribution of the field, but we take a scan along the axis of the antenna, which will be this axis, and vertically we just put a time axis. Right? What you can see very clearly, so this is the beginning of time, so the pulse arrives around this area. So outside, on the periphery of that image, this is why our incident excitation comes in, and it excites basically these waves on the antenna. And what they do, they start moving along the surface. And if they start moving along the surface at a different point of time, they will arrive a little bit later. And that time domain time domain time domain representation of that field actually shows us kind of chevron-looking patterns. And that's the motion of the wave starting from the edge, and it moves towards the center. It could go over the other side or reflect part of it. And then it interferes also with all the other waves that start at different parts of the antenna. And as you could see, as the time goes on, it creates this sort of almost like a checkerboard pattern, which is basically a resonance, because waves coming from different sides of the antenna, they start interfering with each other. In some places they form constructive interference, some places they form destructive interference, and they form this resonance. Right. Now the pulse has already kind of decayed by picoseconds 3 or 4, but actually some oscillation still remains on the antenna. So it's excited, and then just like the waves on the water, you'll have a little bit of oscillation of waves going back and forth, back and forth. So this is just to illustrate what happens on most of the metals when they are excited with electromagnetic waves. Okay, so if this technique is sensitive to the surface plasmon waves, then it could be applied to other objects. This is an example of a carbon fiber. You can think about it as a piece of graphite. It can conduct in this direction. It does not conduct very well in the opposite direction, but it basically can sustain current. So in principle, it should also sustain the same type of plasmonic oscillations. Now, if you place that probe with an aperture behind it, just underneath of it, you'll see that in principle it should pick up this electromagnetic waves. What's quite interesting, even though the waves might be pointing towards the metal, it actually can still couple to the aperture and therefore be a detector. So we try to investigate these type of objects. So it's already smaller, maybe only about 6 micron in diameter, but still fairly long. So it actually can sustain several oscillations of electromagnetic wave along it. Right? So, and if you take an image of this carbon fiber, you'll find that there are areas where there's a forming like a standing wave pattern with different polarities of the field. Right? So this is an image taking at specific instances of time when the resonance already has formed on the carbon fiber. You can also look at it in time domain, similar to how we've done it with the bow tie antenna. And likewise, you could see that the wave starts right at the edges, actually right underneath of the carbon fiber, right at the moment of the arrival of the pulse. Actually, the fiber blocks the aperture completely, so there's no wave in the beginning. The only time it arrives, the only time you could actually detect it, when it arrives a little bit later, starting from the edges of the carbon fiber. So it really is excited at the edges and then moves along. So it's really very good illustration of surface plasmon wave propagation. And you can also determine the speed of propagation or dispersion relationship for these plasmons directly from this type of measurement. So if you also want to look at the resonance, you can take a Fourier transform of these waveforms that are detected basically with and without the carbon fiber. And you can see that they actually clearly show resonances. This is the first order resonance right here, and this is the second order resonance. That's the one that we saw with this type of a distribution. Right. So it's about 3/2 of the wavelengths kind of sitting on this resonance. Okay. Now, so far it's been metallic objects. What about the dielectric objects? And this is also interesting observation that we made. So there was a few years back, there was an idea of trying to make what we call metasurfaces. Metasurfaces is something that where you can engineer electromagnetic response on a sub-wavelength scale by using either antennas, very small metallic antennas, or dielectric objects. So similar to metallic objects, dielectrics can sustain resonances. But one requirement for that is they tend to need to have a very high refractive index. And we found a very good candidate for that. It's a titanium dioxide sphere. In fact, this is one of the most common object that you can find. They put it in paint. It's basically something that disperses light. It looks just white. But it has very high refractive index with dielectric constant at Terahertz frequency. So it's an ideal candidate to see whether this type of object can actually resonate. Now, they are much smaller than wavelengths. If you try to put this object in a Terahertz beam, you'll find out that there's practically no noticeable effect on the Terahertz wave from this object. It's just too small. It scatters very little amount of light. So it's going to be less than 1% of absorption in that electromagnetic wave. So we were wondering whether this near-field microscopy technique can actually help to detect those particles and therefore characterize the resonances. It turns out that if you place this dielectric sphere just directly above that small aperture of the near-field probe as we were discussing, it significantly enhances the transmission. As we discussed, very little light passes through it. And one of the reasons the light doesn't want to go through the aperture is because of the boundary conditions at the walls of the metal. But if the object itself confines electromagnetic wave through whether it's high refractive index or some sort of resonance, it actually bypasses that boundary conditions a little bit and effectively helps to pass electromagnetic wave through this aperture, which makes the detection of this object actually quite favorable, because what you'll see practically no light passing through unless the object sits right in front of the aperture. So that would be Terahertz image of this object. You see there's practically nothing here, but then at one place where the object is, it changes significantly the contrast. And what's interesting, it only allows that to happen at one specific resonance frequency. So it's clear that an electromagnetic wave that contains lots of frequencies, so it's this very broad pulse, actually excites the resonance, and through that resonance, it couples through the aperture, and we have a sharp peak in transmission. And through this, we can actually calculate the refractive index of this material and very precisely characterize these objects. Okay, so now that we understood it was possible to look at individual objects, suddenly it opens up the field to investigation of the whole range of different type of resonances. There's another interesting resonator which contains two metal, what we call a double metal resonator. What's quite nice about this, it actually is a deeply sub-wavelength and contains all the energy typically between those two metallic bars. And even though most of the energy is contained there between the bars, so you can't really quite access it, but the probe is sensitive enough to actually pick those resonances, and you can detect them. You can characterize exactly the frequency at which this resonator resonates. So we've done lots of other investigation of resonators since the field of nanomaterials has been growing, and it actually showed quite a lot of interesting investigations there. For example, you could detect modes on the resonator that tend to be very difficult to detect, what we call dark modes. And a dark mode, by its nature, if it's excited, it tends to stay on the resonator. It does not radiate efficiently. But if you bring a near-field probe right next to it, then as a result, you can pick up the waves of this non-radiative mode and actually detect it. And we've recently been doing investigation of this, and what we also understood is that there actually is a very simple interpretation of the images that we receive through this technique. It actually simply directly corresponds to the current that occur on the resonator because of the surface plasmon motion, right? So we call it surface plasmon previously, but in reality, this is still current. So electron charge moves back and forth within the resonator, right? So even though very often this type of techniques that include either aperture or some other technique to pick up these evanescent waves, they tend to be very difficult to interpret. So people spend quite a bit of time just to understand what that image means. But with this and with a lot of modern electromagnetic simulations and modeling, we're actually able to understand what is it that we see. In this case, it basically shows the distribution of the current that occurs on the resonator. You can see, depending on the mode, very different patterns of the current. In case you are not that familiar with electromagnetics or modes or resonators, it is pretty much like a standing wave pattern. If you're more familiar with water, you can imagine if you have a bucket of water, there will be resonance with a particular sort of periodicity, and that's a mode of that particular system. Similar on these metallic resonators, there will be modes which have specific patterns, and that's what is possible to detect. What's also quite important to notice, these patterns usually is impossible to detect in the far field. They're all sub-wavelengths, and because of this diffraction law, actually you cannot really see it. Even if you put a very expensive good microscope, actually you will not see this pattern. This only occurs within a very small distance from the surface. Okay, so we can now excite resonators, dielectric or metallic, and it's very, they produce good signals. Can we go a little bit further? These still tend to be defined by the wavelengths. So, more recently we've done the next step by trying to use the resonator to confine the field even further to a much smaller size. So metals tend to confine electromagnetic waves. This example of you could take two needles and you pass electromagnetic wave, try to pass between them. They will, because the boundary conditions of the metal, electromagnetic waves cannot really go into the metal, so the charges will be induced on the surface, and they will basically concentrate all the field in the volume when there is no metal. So, for example, this two needles converge to a single point with a little bit of a gap. There's going to be very strong enhancement of the field right into the gap. So what we try to do is place an even smaller object in this gap. In this case, we placed an indium arsenide nanowire, very small object. It's about 100 nanometer in diameter and a few micron in length. And that, with an antenna, brings the terahertz field right in this region. And the question there, well, can we actually, with this concentration, detect it? So we set up these experiments with people who actually, the audience is great to see. So Tom, Sarah, James, all contributed to this work. What we see is, so imagine electromagnetic wave incident to this dipole antenna with indium arsenide nanowire right in the middle, so it concentrates the field here. And then we place this aperture and it picks up those evanescent waves that travel along the antenna. Right, and then it could be detected later with the near-field probe. So as we said, we can detect resonances on the antenna. So now the question here is that if that nanowire is present, it is going to change the resonance. And it turns out even such a small object will slightly change the resonance of this bow tie antenna. And it's actually possible to detect. So this was a resonance form on the bow tie antenna. Right? And in the next slide, I'm going to show changes that happen. So this is a change of this waveform. What you see is additional oscillations happening. And the interpretation of this result is basically it's change of this oscillating resonator because of the presence of the nanowire. And if we actually calculate what is the effect of this nanowire, it's only 200 additional electrons placed inside of this nanowire that will cause this change. And it's possible to see it. And that is done just because, first of all, we're sensitive to the surface plasmon waves traveling over this antenna, and then a small perturbation of the geometry actually changes the resonance properties of this antenna slightly. So with this, it actually kind of allows to move to completely new, much smaller type of objects that you can investigate with this technique. Something that back 20, 30 years ago would be completely unimaginable to try to do it. But slowly, bit by bit, with developing of various technologies, actually became possible. Okay, so if we look again at this space that we have, right? Over the years, we've done quite a bit of various imaging experiments. just try to understand what we see, how different objects interact. And we've learned quite a bit about how we would see this world in terahertz light. So what else can we do? Actually, together with the development of just image instruments, since there was no technology for the detectors, we have to build our own detectors, have to build our own sources of terahertz wave. You kind of have to develop all the technology with it. And as I mentioned earlier, in order for this technique to work, we needed to have detectors that are very close to the aperture, which means that they would need to be made very small and placed very close. So over the years, we actually spent quite a bit of time developing those terahertz detectors and actually developed a range of various terahertz detectors based on nanowires, two-dimensional materials, as well as strongly modified semiconductors. Just with the idea that we need to make them smaller, but actually with this, we also, along the way, developed very efficient terahertz detectors. This is some of the work. This is some of the examples of the detectors that we use right now. So they're not using a very simple material as we used before, but quite an elaborate structure made of semiconductor. What's quite interesting about this type of structures, even though they look almost partly transparent, so the white areas in this image is material, low temperature chrome yellow arsenide, and the dark area is basically where it's not present. So it looks like a mesh. But quite interesting, because of the electromagnetic resonances that it can sustain, each of this cube can sustain this almost looks like a donut-shaped electromagnetic waves. And if you get them just right, you get two different resonances with different symmetry, they tend to absorb all the light. So it basically becomes completely black at that particular wavelength. And it requires much smaller, the amount of material it requires is much smaller than we would normally use for this material to absorb a reasonable amount of light, which means that we can make it much smaller and absorb it very, very efficiently. So it turned out more like a side project, but actually it's quite interesting to discover this type of structures. All right. So how far could we go with the size of the aperture? As I mentioned, the smaller the aperture, the eventually basically ran out of signal. The electromagnetic wave does not want to pass through a very small aperture, but we can get to about 2 microns, which is more than 100 times smaller than the wavelengths of light, which is actually quite difficult to do. Right, so where am I now? I wanted to maybe do a couple other examples. How are we doing on time, by the way? Am I too late? Am I?
25.
Is that right? Try to wrap up quickly. So there's a couple of other examples maybe I wanted to discuss. So maybe they're not requiring very, very high spatial resolution, but it's still one of the ways of imaging terahertz electromagnetic waves. Waveguides. We all, as electronic engineers, we all need waveguides to deliver electromagnetic wave from one place to another. And in terahertz frequency range, if you're just developing this new area, you'll find that actually there's no really good solution for waveguiding at that time. So we looked at a couple of waveguide solutions that actually use this imaging technique to not only to characterize the waveguides, but actually visualize the modes that travel in the waveguide. And using the temporal evolution that we can detect, it's actually look at dispersion. This is an illustration of which you could measure. If you send that very short pulse through a terahertz waveguide, it comes as just one single cycle. But because different frequencies travel through that waveguide with different speeds, it kind of disperses and it changes the frequency as it goes along. So that single oscillation actually splits in hundreds of oscillations. It starts with very fast, and you can see it slows down later. And what you see here is, as a function of time, different frequencies arrive at the end of the waveguide at different times. And that's what we call a dispersion of the waveguide. So it actually, one of the most fundamental properties of any waveguide is what is that dispersion, and it could be measured with this type of technique quite easily. Now, the imaging itself was also quite interesting. Different modes in the waveguides travel with different speeds. And as you can imagine this, when the single pulse enters the waveguide just as a very well confined single cycle oscillation of electromagnetic field, as it goes through the waveguide, first of all, different frequency travels with different velocities. Secondly, it also splits in different possible modes. Right? So you could time at different moments in time and actually detect different modes coming out of the waveguide. So in a way, you just enter here, but at the output, you'll see this different field distribution that actually corresponds to the modes of the waveguide. Right. And one more application that we recently been working on is we've also been looking at the generation of Terahertz waves. Those pulses that I've been using so far in this lecture, they also need to be somehow generated. And there are different techniques how to do it. And one of them is to excite semiconductor material and create photocurrent, very fast photocurrent. If you study a little bit of electronics or electrodynamics, you'll know that change in the current will radiate, produce electromagnetic radiation. And this is the type of phenomena that is exploited here. When an optical pulse falls on a semiconductor, it creates electron-hole pairs. And there could be mechanisms by which those electron-hole pairs starts moving with preferential direction. Very often, they cancel out and there's no emission, but you can set up those conditions, but actually there will be preferential current. And then that current will radiate. So normally, we don't really know what happens at that process. What we wanted to do here is just simply look at this right on the surface of the material to see whether we can detect different distribution of these currents. And actually, it turned out it's possible to see. So this is an example of optical excitation falling on the semiconductor. So it has sharp edges here on the right and the left-hand side. But it turns out most of and then we simply detected the electromagnetic field that's being generated by this photoexcitation. So it turns out right at the edges of that excitation, this is where this non-equilibrium current occurs, and it radiates electromagnetic wave. What's interesting, if you do it on directly at normal incidence, so you have these edges on two sides, and this is the pattern that you will detect of emitted Terahertz field. And it's anti-symmetric, so wherever there is red, on the opposite side there is blue. And again, so this is happening in the near field, very close to the surface. If you look at a far field, actually this type of a pattern just cancels the electric field out. So the electric field with one direction cancels the electric field with the other direction. And as a result, when you do this experiment, you normally in a far field, you would not see any Terahertz emission. But actually, there's a significant amount of Terahertz emission because of this non-equilibrium current right at the edges. It just happens in the far field, it cancels out. So if it's possible to create some sort of asymmetry and in this distribution, something like that, and then the cancellation will disappear, and actually you could use it as an emitter of Terahertz wave. And that's another example of same pattern with slightly wider illumination. You can make it wider. You can see this blue area just starts getting wider and wider. You can build up that electromagnetic emitted wave that's now asymmetric. Asymmetric could be used for sources of Terahertz pulses. This actually continued in much more elaborate work when we started also using different mechanisms for generation. You can see you can nanostructure the semiconductors in certain different ways to effectively generate Terahertz wave, and also to control. So this process, it's a photocurrent. So normally it's defined in one particular direction. But if through design of this nanostructure you can actually modify it, then you can start synthesizing again next level devices. And in this structure, for example, we realize it's possible to change the polarity of the pulse. If you change the polarity, you can start doing optical devices similar to, for example, a Fresnel lens. Right? And another investigation also just recently figured out how we could do this also by changing the phase of the terahertz. So that gives even more opportunities to utilize this in cases. And this is an example of this type of a device where it basically has a nanopatterned material deposited on, or in this case, attached to just transparent substrate, and if you illuminate it with an optical beam, such that different areas will generate terahertz field with different polarities, you can actually create sort of structured terahertz wavefront. For example, you can focus the beam at one spot. So this very simple, very compact, flat device generates and focuses the terahertz waves in one place. This experimental image of this focusing happening, you see it right in the beginning. There is just a white front, but as you go a little bit later in time, you can see how different waves coming from different sides actually combine to all this region. So that's really the focus terahertz beam. All right, so with this, I'm getting close to the conclusion. What I wanted to say is that with this developing of this technique, originally just simply trying to find out, can we possibly improve the spatial resolution for terahertz imaging? We kind of slowly build up a whole catalog of different type of phenomena that we observe with this technique. And it does allow you to kind of understand better what is happening this frequency range when electromagnetic waves interact with semiconductors, with metals. So it does actually give you better understanding what this electromagnetic part of the spectrum can give you. And hopefully all this will eventually be using future terahertz devices and future applications. There's a lot of people who've been contributing to this work. So it's not only my work. Most of it has been done here at UCL with a large number of people. So there's the whole UCL people. I'm really happy to see quite a few people here sitting in this one of the front rows. I also was blessed to collaborate quite a lot of people across the world. I have colleagues in Europe, in Italy, with friends here in UCL, VT, colleagues in the United States, in San Diego National Laboratories. It's actually really been a pleasure to work with so many talented people. It's exciting, it's exhilarating, it's always very, very interesting. So all this work that I showed, it's a reflection of the effort of all those people. And so I'm very grateful that I had a chance to collaborate with everybody. And also would like to thank the funding agencies that support the report, supported this work, especially the Royal Society. That I was also very I'm blessed to have the Royal University Research Fellowship from the Royal Society that really helped me to focus on this research, and also as well as my parents who encouraged and probably nurtured interest in sciences and technology. So with this, I'll close and welcome your questions.
I know it's between us and refreshments, but we have time for maybe one or two quick questions. If anyone wants to ask? Helena.
So, completely not on the lecture, but recently there's been a big push to view terahertz as a way of, everybody's obsessed with AI and energy reduction, even though, optical interconnect's tiny part of the overall energy. And to use terahertz because the frequency is lower, therefore HF is lower, as a communication channel. So you need waveguides, of course these will be bigger. What do you think about this application?
Great.
She's an next glance already.
You'll need very big fibers, no?
Yeah, no, but depends on the application. I think it's fine. So the waveguides I was showing, right, it's actually a hollow glass fiber, right? So it is.
Which glass?
It's a hollow glass. So it's actually it's a hollow tube, just coated with metal and dielectric. and it is, even though it's glass, it's
Flexible.
small enough, but it's flexible enough too. So it's actually just as flexible as an RF coaxial cable. So it's possible. So the thing is, look, it's the technology, right? It's sometimes with things like there's no way it's going to work. Like,
Is it exciting? Do you think it's exciting?
Everything is
Agreed.
Thank you for your nice talk. I would like to ask about the mode of the TiO2 particle, because if this is a lower order V resonance mode, usually you will have a different kind of wavelength or a different kind of line width of the mode will mix together in a very close region. If this is a whisper gathering mode, usually you have many high line width modes standing with an equal spacing, but I think the nanoparticle doesn't show both features, so I'm very curious about the particle itself.
Thank you for the question. This is going into very, very detail of this.
Just want to discuss over drinks.
This is actually classical magnetic dipole mode. So it's the first order media mode, magnetic dipole. You could see this little bump. This is the electric dipole mode. This is the magnetic dipole.
Okay, so this is a magnetic dipole. That's why it have a high Q factor.
Yeah, it has a high Q, and it's pretty much one wave along the circumference.
Yeah.
Right. But thank you. This is much more detailed questions. Yes, but it is actually what's really nice about it. It's there's the electric sphere. The dielectric constant is close to 80, so very high refractive index. So it's actually very, very much sub-wavelength, and it just has this really classical media mode in there.
Thank you.
So, as is very common with an inaugural lecture, this has been a real tour from, we started at astrophysics and the formation of stars and measuring, and have now got down to nanoparticles and things at the molecular and submolecular scale. So we have covered a whole range and particularly seen some really exciting applications of the things that this technology might allow us to do in imaging in the world of the very small. So I would like you to extend your congratulations to Oleg on a fantastic inaugural lecture. Thank you.
And I very much would like to say thank you for everybody for coming. It's a pleasure to see the full auditorium, and I've like people from very young to much older. It's just
for those that are outside of the department and of the faculty, we run this series each year of inaugural lectures, and the website you probably found out about this will speak of all those from across the faculty, from electrical engineering, but also the other departments. I believe this is the last one of the series for the summer. I don't think there's any more scheduled at the moment, but I'm sure we will start again from September. And next week our new batch of professors will be announced, so there will be new colleagues to celebrate in the upcoming year. And please feel free to join us for a drink and some refreshments in the foyer outside. And thank you very much for your attention.